Hi, and welcome back. In this video, we're going to take a short digression from the main course material to discuss a very important nonlinear circuit component known as the diode. An ideal diode is considered to be the most fundamental nonlinear circuit component, and it is a two-terminal device that looks like this. You have the positive terminal, this is the symbol for the diode, and then a negative terminal. And basically, this device operates as a unidirectional current valve. So if the arrow of the diode is pointing to the right, that means that the diode only passes current flowing in that direction, and vice versa. Now let's look at a plot of the IV characteristic for an ideal diode. So if a negative voltage relative to the reference direction of the diode is applied to the ideal diode, no current flows and the diode behaves as an open circuit. When a negative voltage is applied to the diode, we say that the diode is reverse biased. On the other hand, if a positive current, again relative to the reference direction of the diode, is applied to the ideal diode, 0 voltage drop appears across the terminals of the diode. In other words, the diode behaves as a short circuit in the forward direction, and it will pass any current with 0 voltage drop. And when this happens, we say that the diode is forward biased. Now let's look at a classic application of the diode, which is the rectifier. Let's suppose that we have an AC sinusoidal voltage V in of t applied to our circuit. So here's our V in of t. We then have a diode D in series with a resistor of resistance I. And we'll take the output voltage to be the voltage across the resistor. So when the input sinusoid is positive, this diode will be forward biased and current will flow through the diode in the forward direction. In the ideal case, the voltage drop across the diode would equal 0 volts, and therefore the output voltage will equal the input voltage. So case 1, when V in of t is greater than or equal to 0, V out of t is equal to V in of t. Now on the other hand, when the input sinusoid is negative, so V in of t is less than 0, this diode is reverse biased and it will act as an open circuit. Since no current can flow through an open circuit, the output voltage will be 0 volts. So when V in of t is less than 0, we get an output voltage of 0 volts. Now let's look at a plot of the input voltage and the output voltage. So here's our input voltage waveform. It's a sinusoid at a certain frequency. And so our output voltage during the first positive half period of the input, V out of t equals V in of t. Then once the input voltage V in of t becomes negative, V out of t equals 0 volts, and it stays 0 volts until V in of t becomes back positive. Once V in of t goes through the next positive half period, V out of t equals V in of t, and then once it goes through a negative half period, then V out of t equals 0, and so on. So actually, as we can see from this figure, by placing a diode in series with a resistor and then taking our output voltage to be across the resistor, we get that V out of t equals, in general, V in of t when V in of t is greater than or equal to 0, and it equals 0 volts when V in of t is less than 0. And this is why our circuit is called a rectifier, since it actually rectifies the input signal. Alright, so the analysis we've just done is for an ideal diode. Now let's take a look at a non-ideal diode. So the most common implementation of a non-ideal diode uses a PN junction. And the IV characteristic of a PN junction diode looks something like this. So let's first look at the forward bias region. So the forward bias region corresponds to when the voltage across the diode is V is greater than 0. So when a small forward bias voltage is applied, only a small amount of current will flow in the forward direction. Now once the voltage across the diode approaches this turn-on voltage of the diode, which is usually around 0.65 volts for a silicon device and around 0.2 volts for a germanium device, the current in the forward direction will increase rapidly. Now on the other hand, the reverse biased region is when V is less than 0. When the diode is reverse biased, only a very small amount of leakage current will flow through the diode in the reverse direction. Once the magnitude of the reverse voltage exceeds the threshold voltage VCK, which is usually 50 volts or more, we get to the breakdown region, which corresponds to this portion of the graph. Now there's different models we can use to approximate this nonlinear behavior of the p-n junction diode. The most accurate model of the p-n junction diode in the forward region is the exponential model. And so in the exponential model, for the forward bias case, we have I of t equals Is times e to the power v over vt. Is is called the saturation current, which is constant, and Vt is known as the thermal voltage, which is also a constant. Now, unfortunately, due to the severe nonlinear nature of this model, it makes it very difficult to analyze. So let's look at a much simpler model, which is the constant voltage drop model. This model is based on the observation that a forward bias diode has a voltage drop that varies only in a very small narrow range, maybe between 0.55 volts and 0.75 volts. So we can assume that this voltage is a constant, maybe 0.7 volts, which is called the forward voltage, and our IV characteristic would look like this. When V across the diode is less than 0.7 volts, no current flows through the diode and it behaves as an open circuit. And then once the voltage across the diode reaches 0.7 volts, then any current is allowed to flow through the diode. Another model of the diode is the piecewise linear model. In this model, when the diode is forward biased above its turn-on voltage, it acts as a linear resistor. And so its IV characteristic looks something like this. So when the voltage across the diode is less than 0.7 volts, it acts as an open circuit and no current is allowed to flow through the diode. And then for voltages V greater than 0.7 volts, the diode acts as a linear resistor. And so in other words, the p-n junction diode can be replaced by an ideal diode in series with a voltage source, in this case of 0.7 volts, and a resistor with resistance ID. This resistance ID is 1 over the slope of the line of ID versus VD, when VD exceeds the turn-on voltage, which in this case is 0.7 volts. Usually this resistance ID is on the order of a few hundred ohms. And as you'll see in the next video, when analyzing the envelope detector circuit, we will make use of this piecewise linear model for the p-n junction diode when analyzing the behavior of the envelope detector circuit when the diode is forward biased.